any spelling error. Okay, but actually last night I just figured it out that I could make the selection for you. So if you click a small arrow next to the box, you will see the true or false, or correct or incorrect. So you just select one of them. Okay, you don't need to type. Okay, so I try to do that. If it is successful, then it's good for you because you don't need to type the true or false or correct or incorrect. Okay, so Kevin, no partial credit again. Yeah, no partial credit, Kevin. So be very careful. Of course, I will make the final exam a little bit easier, but at the same time, you have to be absolutely careful. Okay, follow instruction. If I ask you to keep only one digit after the decimal point or something like that, right? So please do so. If I ask you to write in the box just one word, write in just one word. Don't write two or something like that. Okay. So try to prevent these careless mistakes on your side. Okay, so let's see a few more questions over here. Long, will the final have short programs like last time? I already forget all about midterm number 2 already. Can you remind me what is in there? What did I ask you for the midterm number 2? Life nowadays is extremely busy, and I just forget what I did yesterday. Actually, 3-line C program or assembly. I see. Yeah, you may have code, right? Probably short of them. I don't know. I cannot be more specific on that, but please prepare. Okay, please prepare all of that. So Kevin, how is that going to be automatically graded? So you have to be careful. Okay, so maybe I ask you to write an instruction, add instruction, something like that. So you have to be careful. You have to type in correctly. Okay, so don't. But let's see. I because the final exam will be 2 weeks from now. So I didn't really finalize yet. But that's what I'm thinking. Okay, there are multiple ways to write the same instruction. How is that fair? Okay, so don't worry too much about it. As I said, I didn't really finalize the question, right? So I will think about it carefully. Okay. Final exams are stressful. Actually, really, not really, Kevin. You know why? Because you have a lot more time. I think it's 2 hours and 15 minutes. So I think it's less stressful. So just please check your work carefully, okay? So Rebecca, will the final be comprehensive or just chapter? Will be comprehensive, okay? From chapter 1 to chapter 15. But the focus is more on 10 to 15. But you will find, but I will ask question all over. Okay, you may have short question, you can have long question, whatever, all over from chapter. But the focus will be for the last 4, the one that you didn't do yet for midterm 1 and 2. Matthew, how many questions? Okay, as I said, I didn't really finalize the question yet. Okay, so I don't know. So maybe there are a bunch of them, especially true for question. You may have many of them. Okay. Okay. So any other last question? The good thing is you have a lot of time to review, right? Because the final will not be I think it's until 18 or something, 18 of this month. So you have a lot of times to review. So this is the last time already. Do it carefully, review it carefully for me, everything, okay? What is the best way to review? Slide, book, problems? Yes, slides. All of that, actually, all of that. Slide, book, problems, homework, right? All of them will help. All of them will help. And please come to the review section next Monday, I believe, right? Next Monday. So I I probably will make another review document and send out to you. So it will be useful if you come to the review section next Monday. Okay. Let me see. Okay. So with that, seems to me that you don't have any other questions. Let's start the lecture today. As the last lecture, I asked you to generate the waveform over here, right? The waveform is, the pulse width is 10 microsecond, like this, and the period is 0.655 second, right? So at the beginning of the lecture, it seemed to you is very hard to do. Is that right? Very hard to do that. But I hope that by the end of the lecture last time, you know how to do that. So that's wonderful. So you know what? To control the frequency, to control the period over here, I hope that you remember you can control the ARR value. Is that right? You can control the ARR value. If you set that ARR value, you can control the period of your output, okay? And you can set the CCR value to control the pulse width. Is that right? Okay, so wonderful. You can take just one lecture and you should be able to do a lot of things. So at my generation, to do this waveform, you know what? I actually have to design a chip or something. So nowadays, actually, you can buy a microcontroller with timer, and you can generate this signal to control the sensor over here easily. Okay, that's wonderful. And that's for output. And for today, we will talk about for the input over here. Today, when the sensor send out the signal and the signal reflect back, it will be captured by the receiver over here, and the receiver will generate a waveform coming out of the echo pin over here and sent to your microcontroller, right? So, and when it's sent to the microcontroller, you have to be able to use the timer in there to measure the pulse width, okay? So if you know the pulse width, then you know the distance using this formula, okay? Okay, so if you measure if the pulse width is 580 microsecond, for example, right? So you know that the distance will be 10 centimeters, okay? Something like that. Just use this formula to calculate the distance. So we will learn today how to use the timer to measure the pulse width as well. But before going to that, let's finish the portion for output first, right? I think that last time we stopped at maybe in the middle. So let's continue to finish the output part, and then we will conclude with the input part. Okay. So let's go to. I believe that we stop at slide 12 or some also 8, 9. Maybe review this one a little bit over here. So you see this waveform over here, right? This is very similar to the waveform that I asked you to generate and send to the sensor, right? So you can see the period here is controlled by the 1 plus ARR multiplied with the clock period over here. Actually, I already fixed this one, right? And thank you. I think I remember that's Matthew reminded me. So I already fixed the typo over here. This is a clock over here, CK instead of CL. Okay, so just pay attention to that. Okay, so you can also use mode 2 too, right? Mode 2 can also generate the waveform like that, right? And similarly, 1 plus ARR controls the period of your signal over here, right? And the duty cycle, or the high part, the pulse width here, is controlled by both. I mean, CCR by the clock period over here, and by AAR as well, right? Because the high part here is related to the duty cycle, and you can see that the duty cycle related to all of these, okay, all these parameters that you can use. Okay, so this example we already studied. So let me see. How about this slide? Okay. Oh, this slide is actually instead of still mode 2, okay, still mode 2. But instead of setting to be up counting or down counting, so in this case we set it with we use the center aligned mode. Okay, center aligned mode, and you know that for mode 2, if the counter value is smaller than CCR, okay, the output is low. Okay, if the counter value equals or higher than the CCR, so the output will be high. Okay, for the going up part. Okay, but for going down part over here, there is a slightly different. So be careful with that. So when you go down over here, when the counter value hit 3 is the CCR value, right? The output will be low right away at that time. So you can see even the counter value equals the CCR value, this one, the output is still low because this is in the going down direction. Okay, going up directions, there's a little bit different over here. If the counter value equal to CCR, the output is high. Okay, so look at over here. Just you can see the equal sign over here, and when you go down, you don't have the equal sign over here. That's all. Okay, so pay attention, right? I already gave you 6 pages for you to write formula or whatever. So I think that maybe you can write some formula like this into the cheat sheet, okay, to for you to remember. Okay, so these tiny detail may cause some mistake, right? When you fill out the boxes. So be careful with this one, right? So maybe just copy this formula into your pages, and also prepare some blank pages. Okay, some blank pages for you to write to solve the problem as a scratch pages, right? Because you most likely you just enter the final value into the boxes. Okay, so don't forget that. Okay, so maybe let's do one more example for the center aligned mode. Okay, to see if you understand, and you have to do it quickly. So let's see if you can do quickly. Okay, with that mistake, that's important. If you do quickly and you make mistake, you will get 0 credit anyway. So be careful. Okay. Okay, so let's do this one. Oh, I forget to say the period for if you choose the center align mode, the period is 2 times ARR. Okay. If you use counting up or counting down, it is 1 plus ARR. But if you use center align, that's 2 times ARR, and that makes sense, right? So for example, over here, if you set ARR equal to 6, you can clearly see that it will repeat after 12 cycles, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, and repeat again. 1 over here. See? So the waveform here will repeat after 12 cycles, and you set the ARR equal to 6 over here. So basically, the period is 2 times of the ARR value. So just pay attention to that. And of course, the duty cycle is CCR 1 minus a CCR over the ARR over here. Okay, so let's do that. Let's check to see if you can figure out the period and the duty cycle quickly for the example on page 13. Okay, how about this one? Okay, so ARR equal to 6. So what is the period? Easy, right? 6 times 2, that will be 12 multiplied with the clock period over here. Okay, wonderful. So if the clock period is 2 milliseconds, if the clock period here, the clock the counter directly. Okay, I put this one in to clear out all the confusion. Okay, so if the clock period here is 2 milliseconds, okay, what is the period of your signal? The period of your signal is from here to here, actually, right? Quickly, 1 second, quickly. What is the period of the output signal? Wonderful. Long just get the first answer. 24 millisecond. Wonderful. Yeah, 24. Very good. Very good. Millisecond. Okay. Don't forget the millisecond. However, you know what? In the final exam, I usually ask like this: fill out the box, the period. Just an example. Fill out the box. Just the period of the output signal without the unit millisecond. So don't put millisecond in the box, okay? Just put 24. Basically, you have to follow the instruction exactly, okay? Understand? Yeah. So be careful, okay? So let me see. Okay. So that's the period. How about the duty cycle? Duty cycle, maybe you apply this formula, right? CCR, what is the CCR value in this case? We set 1, right? CCR equal to 1. So 1/6, right? And then 1 minus the 1/6. That's the 5/6. And that makes a lot of sense. See, the duty cycle here is 5 times over here and 1 time over here for load. Okay? Understand? Very good. Okay, so now you understand everything about that. So, very good. So let's move to the next one over here. Okay, so the timer that I taught you in the previous lecture, probably the most important, the core of the timer is the counter itself, right? The 16-bit counter. Okay, but around that counter, you have a lot of things. You have a lot of blocks or registers to support. Okay, to set the counter either coming up or coming down or center a line, or maybe to set the maximum value ARR, right? So around the counter here, you have a lot of things to select. So the timer is not that simple, you know. It has at the center is the counter over here, but around it, there are a lot of blocks to support it, right? And you already know the prescaler block. You already know the this block too, to select the clock source to clock the counter over here, right? And you also know about the AAR block. So there are a lot of flexibilities in here for you to control the counter. So in this case, you can see. So sometimes you can use even the external clock too, right? You can use you can choose the source of the clock as an external clock, or some internal clock generated by the processor, or maybe the output of some, even the output of some timer, you can also fit into here too, right? And then you can use the prescaler actually to divide the frequency down, okay, before you fit into the counter over here. So you have a lot of flexibility. Okay, so now I don't know for the robot you used for the lab, right? How many counter in there do you have in there on the board? I don't know, right? Maybe you remember. I didn't do the lab, so I don't remember. So, but however, this is the one counter over here, right? This is the one counter, for example, right? So now, if I want to have 4 counters, so what do I have to do? Is it possible to use a combination of clock selection? Or actually, you have to select only one of them, okay? Either one of them. You cannot select 2 or 3 of them and fit into here. They will find one another, okay? So let's select one. There's a multiplexer over here, okay, for you to make the selection. Okay, so now if you want to have 4 counter, right? So because the 4 timer, the timers seem to me it is a very useful device, right? So I hope that I wish like you, right? I wish that there would be more timers in the microcontroller for us to use, right? So if you want to have 4 counter, maybe you repeat this one 4 times. But as I remember, this one is actually complicated over here, right? So maybe you have to repeat this one. Well, seems to be that's a little bit expensive solution, right? How about this one? How about this one? Maybe if you want to have four outputs, four separate output, right? Maybe you can share this guy. Maybe you can share the 16-bit counter over here, okay? Right? But you have four of these. You have four of these, okay? So in this case, for example, I mean, maybe you have, or actually you can share this part, but you have four different CCR for you to set, okay? So that's good. If you do so, you can use only one counter, but you can generate four outputs over here for you, right? So wonderful. Instead of one output to control the sensor, if you use this part, then you can generate four outputs to control four sensors, for example, right? So you can see this is actually the architecture of one of the timer that you see we use in some of the microcontroller. It has only one counter, but it has four different CCR over here for you to set, because and then the comparison over here is actually compare the counter value with each of the CCR value over here. So that's why it can generate four signal over here. Okay, so from here you can generate maybe the frequency, the period of the output of this output are the same, but you can control the duty cycle independently for each of them. Okay, so that's good. Okay, so let's move on. So assume that we have, just remember that we have four CCR value over here, right? And all of these share the same counter over here. Okay, so let's move on. So let's see. Okay, so now if you look at over here, I have an example. I just look at the two output, okay? And each output is controlled by its own CCR value, okay? The ARR is common, okay? So ARR is 6 over here, okay? So for the output 1, okay? For the output 1, I set the CCR equal to 3, okay? And I use mode 1 for both of them. So do you agree with me? Do you agree with me that the waveform you generate for output 1 is this, right? Understand? For mode 1, if the counter value is smaller than the output will be high if the counter value is smaller than the CCR value. Okay, so as you can see, it's high over here, and when the counter value equal to the CCR, it go down like this. Okay, okay. So for the output number 2, I have another CCR for it, and for that one, I set the CCR equal to 6. So, and also mode 1 too. So you can see that the waveform you generate for the output number 2 will be like this, right? Easy to understand. Is that right? The period for both of these will be 7, right? Will be AAR plus 1. But the duty cycle for this one is different from this one. Okay, so use the duty cycle formula you learn from here, right? Mode 1, mode 2 has a different formula, so be careful. And you can figure it out to see if the duty cycle is like this. It's very easy to understand. Okay, so let me come back here and read a few questions here to see Matthew. FPGA, you would have to set up the clock. Actually, nowadays you can use FPGA to generate this waveform as well. So the FPGA nowadays is very complex too. You have you can even burn a processor in there. A processor, you can have logic in there, and you can have timer in there too, right? And I believe that you can actually make some selection between the clock source, okay, right? Or you can even take from the clock from an external the crystal oscillator, right? It's a very precise. And because for FPGA, you have a lot of flexibility. Even you can even design a clock divider, frequency divider by yourself. Okay, so for FPGA is actually your design, so you can do a lot of things about that, and you can generate tons of a lot of output waveform. And actually, my research at Stanford, I use FPGA to generate the output to test our chip. So when the silicon come back, when our chip came back, we actually bought a FPGA board and wrote a program to generate the input signal to control our chips. And then we also use the FPGA to measure the output too, to check to see if the output of our chip are correct. Okay, so that's a very powerful device. Okay, FPGA. Probably if you study if you get into the master program anywhere, you probably will. And if you follow this embedded engineering area, and even machine learning, probably you have to deal with the FPGA a lot. So let me see. So pretty much you can do anything with FPGA, writing program using Verilog, right? Exactly. Right. That's right, Matthew. It's a very so instead of designing a chip is very expensive. It may cost $10 million. Okay, for manufacturing, for design time, for testing time, right? So FPGA is basically somebody already designed the chip for you. So the two companies before, I think it's Altera and Xilinx, right? They basically design the chip for you, and you just program the chip to make the general chip to your chip, right? However, because for FPGA, it has a lot of flexibility, right? For it is programmable, so it is actually slower, maybe 10 times slower than the chip that you actually design. Okay, but it's cheaper, much cheaper, right? And so if you want to do a prototype for your design, so usually you use FPGA, or maybe in the case that I just tell you, you can use FPGA to generate the inputs to test another chip, for example. That's going to be very good. Okay, but if you really want to design a high performance system, then probably FPGA is not the right one. Okay, so the highest performance. In that case, you have to use ASIC port, right? Application specific IC. So because it's about 10 times faster. So for example, for machine learning, for example, right? If you really want to have a very high performance, probably you have to design your own chips instead of using FPGA. For example, Google, right? Google has the TPU, tensor processor unit, right? However, Microsoft also tried to use FPGA to do the machine learning too, right? So it's okay with some not high demanding applications, but for the highest performance, probably it is not probably it's better to use ASIC instead of FPGA. Okay, so let me go back to the lecture over here. So if you pay attention, this example over here, right? Basically, you use two of the channel over here, two output over here is right, and for each of the channel, you set differently. You set the CCR differently, and you can generate the two signal over here, right? If you pay attention to these outputs over here, what can you tell me? What can you tell me? If you look at over here, what do they have in common for two output, OC1 ref and OC2 ref? What do they have in common? Yeah, please respond. Wonderful, Shan. Wonderful. Wow, you see that very quickly. Exactly. For the rising end over here, they are alive. See, right? So that's why we call in this case in the mode one over here, they are left edge alive. Okay, left edge align over here. Of course, the right edge on the right edges for these two output are not aligned because you want to control the post width differently, right? But the left edge are aligned. Okay, wonderful. Yeah, so see that one. Okay, so how about this one? How about if I use mode 2? So as you already learned mode 2. So if I set the different CCR, this CCR is used for output number 2 over here, and this CCR is used for the output number 1. And if you use the formula in the previous slides, and you can figure out the waveform here easily. You can figure out the waveform, you can figure out the period, and you can figure out the duty cycle easily for each of them, right? Wonderful, right? Okay, so again, same question. What do you see that in common for these two? Okay, I don't need to wait for you already because there are a lot of hints already. So in this case, you can see that the falling edges for these two outputs are aligned. See, they are aligned over here, right edge aligned. Okay, understand? How about this guy? How about if I move to 17? So if I use the center aligned mode, okay, center aligned mode, and for each of the output over here, I will set the CCR value differently for them, and you know how to calculate the period and duty cycle already, and you know how to plot the waveform. So you will see that the waveform for the output 1 will be like this, and the waveform for the output number 2 will be like that. Okay. So now you see that for these two output over here, they are center aligned, right? They are center. So you can see these edges are not aligned anymore. Okay, but they are center aligned. So if you use both four channel over here, okay. So in this case, 4 of them will the left edges of 4 of them will be aligned. Okay. For this case, the right edge of all 4 outputs will be aligned. But in this case, none of the edges are aligned. Okay. So I remember Matthew or somebody last lecture asked, so what is there any advantage of using center align or left edge align or right edge align? So maybe you can answer that question for me. Anybody can answer that question for your friend. Don't worry, it's wrong or right, it doesn't matter. Any suggestion, please respond. I'm waiting for the answer. Anything, any suggestion? Wow. Just silence, huh? Is it a hard question? Maybe I should put this one into the multiple choice question then. You should answer it now. So let me see. Okay, the first response coming in. Oh, could you please wait? Somebody, what is it? Yeah. Hello. Yeah. Oh, what is that? Could you repeat again? Oh, could you please call back because I'm in the middle of a lecture. So I will finish the lecture at 2:45. Yeah, so you can. No problem. Okay, thank you. Okay, bye bye. Okay, sorry about it. Okay, so let me read the question over here. Can center align be used for distances and equal? Oh yeah, of course. As long as you generate the pulse over here, right? Remember, the requirement for the sensor is 10 microseconds. So whatever you control, you can, as long as you have 10 microseconds over here, that will be fine. Okay. But in that case, actually, you need only one output, right? So let me see. Maybe right edge can be used for flip flop. Okay, how about this one? At least I can see one advantage of center align. Okay. So for example, for your system, for example, right? You need four outputs to control 4 wheels of your robots, your robot car. Okay, understand? And for each wheel, you have to have a different duty cycle, right? To control the speed, right? Okay. So basically, you have to send 4 outputs to the robots. Okay. So imagine the power supply for the robot is from battery, right? So in this case, if you have 4 outputs and all of them switch off at the same time or switch on at the same time, you can see that's not very good, right? It will generate a lot of noise. Is that right? Suddenly you turn on all 4 signals at the same time. Okay, and then the power supply may drops actually because you turn on 4 motors at the same time. So first of all, the power supply may drop and affect the functionality of the robot. The second, you may generate a more noise in that case, right? But in this case, in the center align, these edges are not aligned, right? So the turning on time and turning off time are different, right? So basically, you stagger the turning on and turning off time for these signals. So in this case, noise will be less, right? And the power supply may not droop that much. So in this case, at least in this case, is more useful. You see one of the advantage of the center align mode. Okay, maybe just remember one is okay. So during the life of an engineer, probably you will find more cases in which you can take advantage of the center align. Maybe you know what? Maybe edge align may be useful for something else, right? So it depends on your application. So, but in this case, I just talk about in this case, in the case for robots, in the case of noise and power droops, then maybe in this case, center align is better. Okay. So let me move on. Okay. Okay. So we are done with the output part. So let's move to the input part. Okay. So how do you use a timer? How do you use a timer to measure the pulse width of a signal coming in? Okay, of the signal coming in. Luckily, you can use the same timer to do that job. You just set these parameter, these register, differently. That's all. And different mode you set in. Of course, you have to set. In this case, you have to set the input mode instead of output mode, right? And you also set these values for me. Okay, so the diagram for the input capture is this one, right? It's the same thing, the same timer counter over here, right? And you also have the clock source over here. This is the same block as for the output block. You also have the prescaler to divide down the frequency before you clock the timer over here. Okay, but the difference is this. For generating outputs, the CCR register is used to compare with the timer value. Is that right? Right. But for the input capture feature over here, it is used for different purpose. Okay. So whenever the timer detect an edge, okay, detect an edge of the input signal. For example, if it detect the rising edge, right, or falling edge of the input signal, it will capture the value of the timer into this register. Okay, so in the input case, the CCR value is used to store the timer value at the time at the rising edge of the input signal, or at the falling edge of the input signal, right? So you may ask me, so how can you use that one to measure the pulse width? The idea is very simple, The idea is very simple. So assume that the timer count from 0 to 10, for example, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and when the input signal come in, when the timer value is 2, okay, so you record the number 2 in here, okay, and save that one into the memory, okay. So when the input signal makes a falling edge, right, the timer will capture the value, the counter value at that time too. Okay, so assume that at the falling edge, the timer at that time, the timer counter at that time is 7. Okay, so you can capture the 7 too. Okay, so last time you captured 2, right, for the rising edge, right? So now you capture the value of 7 at the falling edge. So from there you can figure out the pulse width, right? You just take the difference between the 2 counter value. So you just take 7 minus 2 will be the 5 cycles in between, right? So if each clock cycle here is 1 second, for example, right? So the pulse width of the input signal is 5 seconds. Is that right? Understand? So that's the idea. So for the input capture feature, so when the timer detects the edges of the input signal, you try to capture the timer value at that time, and from the values you capture now and the value you capture last time, from these two values you can figure out the pulse width or the period or whatever. So if you look at over here, you will see the idea. Okay, look at next one over here. Okay, so for example, in this case, you use the timer to capture the timer value at the falling edge over here, right? And you also capture at the rising edge over here, right? So you have two value over here, right? And you just subtract these two values, and you can figure out the pulse width over here, right? So very similarly, you can set up over here, capture at the rising edge over here, and capture at the falling edge over here, and you can figure out the width of the pulse over here. Okay. So another example is in this case, you want to measure not the pulse width, but you want to measure the period. The period is from here to here, right? So that's why you will configure the timer to capture at the rising edge only. So you capture over here, and you capture over here, just the rising edge. Ignore the falling edge over here, right? So from these two values, you can figure out the period of the input signal. Okay. So similar over here, you can capture the falling edge over here or the falling edge over here and figure out the period as well. So that's the idea. Okay, that's the idea. Okay, so let me see if any other question over here. Maybe an advantage is if you get several oscillating signal and wish to focus at the peaks, drops. William, maybe this question is related to the edge aligned signals, right? Not to the input capture. Is that right? Okay, so yeah, you can, of course. I mean, if with your creativity, I think that you can use that feature to apply to a lot of other applications. I just brought out one of the advantage, right, of the center align over to the edge align. But maybe some other application, maybe edge align is better then the center align in different aspects. Okay. So let me move. Okay, so for this, how do we figure out the slope of the rising? Was wondering in the case that we do. This is actually digital world. Okay, so we don't measure the slope over here. Okay, so we just measure the frequency. So in case if you really want to measure the slope, probably I think that you can use the ADC, for example, right? Analog to digital converter. You can sample this one at many points over here, and you can figure out the slope over here. Okay, so but not in this case. Okay, in this case, we just want to measure the post width of the period over here. Okay, okay. So let me move to here. Okay, so this is a good picture to see what is going on when you detect some event from, for example, external signal over here, right? So this is the clock signal that's sent to the counter over here, and this is the external signal that you want to measure the pulse width, for example, right? So you usually have an edge detector. Yeah, the edge detector is here. This is actually a more complete of the input architecture over here, right? But let's look at the simpler one first, and then we go to the more complex one. Okay, so it will go to the edge detector that I just mentioned over here, right? So either is detect only the rising edge or falling edge or both, right? And when it detects the edge, right, it can tell the timer to capture the value at that time, to capture the CNT value and put that value in the capture in the CCR register, okay, into that register. And at the same time, if you enable the interrupt, it can generate an interrupt for you, right? To tell, and you can write an interrupt service routine to do something with that, right? To do something, for example, when you detect an edge over here, the interrupt, the service routine can do, like, for example, can ring a bell or something to tell you, okay, I just detect a rising edge from the input signal, something like that. It's up to you, right? So as I said, and I remember that in chapter 11, you know how to enable an interrupt, right? Remember, enable and disable interrupt. Okay, so use that concept, and in this case, you can enable the interrupt. So whenever you the edge detector detect an edge over here, it will generate an interrupt for you. Okay, but remember, you can also enable the capture over here for the timer to capture the value of the counter into the CCR. Okay. Okay, so let's look at a more complicated architecture of the timer for input. Okay, so first of all, this is the input signal. Will go through all these blocks. Okay, so the first block is a filter, right? Because remember, for example, in the lab, when you deal with a robot, usually you have to press a switch or something, right? So that signal, the signal generated from the switch, is not a clean signal at all. So when you turn off the switch, for example, it doesn't make a very nice falling edge from high to low over here, but actually the signal is actually bounced up and down for a while. That's really bad, right? So maybe you may capture the signal in between. So that's why the future that's why for the case of input over here, we put a filter over here, right? And you can control these 4 bits in the CCMR register to tell this block to wait, okay? To wait until the input has been settled down, right? So you have 4 bits to do that. You can set differently. So either it's a wait maybe up to this point only, but if you really want to be sure, maybe you want to wait for a longer time, right? A longer time, and in that case, just change this bit, and that's all. Okay, you can read the manual for about this 4 bit and set it differently to pick a different wait time. Okay. So and then after going through the filter over here, it will go to the edge detector, and then we already talk about the edge detector just a few minutes ago, right? Rising edge or falling edge. So you understand this one already, and how to set the rising edge or falling edge capture. You can use these 2 bits, okay, CCNP and CCP in the CCER register, right, to control the edge over here. Okay, so after going through this one, it will go to another block near input prescaler. Don't be confused with the prescaler block we use for the output to divide the frequency down. Okay, don't be confused with that. So in this case, just to tell you, you use these 2 bit to tell to tell the capture over here. Or should I for example, if you set these 2 bit to be 0, then it will capture every edge. Okay, but if you set equal to 1, for example, it will capture only every other edge. Okay, or every other 4 edges. Okay, so that's the effect of these 2 bits over here. Okay, so and then with that, after going through this one, it can tell the timer to capture the CNT value and put into the CCR register over here. Okay, or if you enable the interrupt, it can generate the interrupt request over here. Okay, or if you set the direct memory access, it will also generate the direct memory access request over here. Probably we didn't really talk about direct memory access too much in Discord, right? So don't worry about that. I guess that I mentioned about the direct memory access in chapter 1 or chapter 2, but since then we haven't talked much about that at all. Okay, so don't worry too much about this one. So do you see the architecture of the timer for the input feature? Okay, and we also already talked about the filter over here, right? So I already talked about this one. So with that, I think the lecture part for EE120 is complete at this point. And I'm very glad that a lot of kudos go to all of you, right? So it's amazing that we can last to this point, 2 months online, and many of the very tough chapters. For example, interrupt, and then floating point, fixed point, right? So and you can overcome all of that. So that's wonderful. Yeah, that's right, Kristen. It's been quite a year. That's correct, right? So I probably, if you want to ask me a few questions, I can do that too. But if not, then we can wait until next Monday. Okay, so I have to create the final exam first. I have to create all of that. So the last thing. So don't forget to fill out the teaching of evaluation form. Right? I just received from the department, the EE department, that you need to fill out the teaching evaluation. I don't know how to do that from your side. So probably I will forward that email to you. So probably you know what to do from there. Maybe they provide a link or something. Maybe I cut a paragraph from that email and send to you through Canvas email. Okay. So with that, do you? Oh, by the way, the deadline for teaching evaluation, I think is 12. So you have only 6 days to do that. Okay. Without any final questions, or you want to stop right here and wait until next Monday? Let me know. Is there any final question?